get this information. You are recording this meeting. Be sure to let everyone know that they are being recorded. All right. And I'm going to share my screen. Hold on. First, I want to spotlight me. Yeah, I don't really know if that helps or not. Spotlighted video. What? It definitely said it wasn't getting recorded. What? Stop spotlighting. Okay, hold on. Let's try it again. Your video is spotlighted for everyone in the meeting. I don't know. Okay, I'm sharing it anyway. And we are doing circuit theory laws. Okay, slideshow. Hello. All right. Circuit theory laws. Everybody see that?
Not yet.
If you haven't finished your component identification lab, leave some room to finish that up. This is the big lab. So this is the lab that's going to cover, you're going to design circuits by figuring out hand calculations and things like that. You're going to design circuits on a program, hopefully multi-sim, that I'll teach you how to do. And then you're going to wire it up and kind of compare all of your answers between the 3 different methods to see how close we can get to the same thing. It's going to be fun. All right, circuit theory laws. So this presentation, we're going to review voltage, current, and resistance, which we've already got. We're going to review, and then we're going to apply Ohm's law. Review series circuit, and then we'll talk about current in a series circuit, resistance in a series circuit, and voltage in a series circuit. Then we'll review and apply Kirchhoff's voltage law. Then we're going to review parallel circuits, current, resistance, and voltage in parallel circuits, and then Kirchhoff's current law. All right. So some of this we're not going to have to write down because we already have it. But just when we get to that point, I'll tell you what we need to write down. So the basics of electricity is an understanding of that electricity requires the understanding of 3 fundamental concepts: voltage, current, resistance. And there is a direct mathematical relationship that exists between them. Does anybody know what that relationship is called?
What?
The mathematical relationship between voltage, current, and resistance.
No.
Oh, wait, who said that? Ohm's law, yes, it's Ohm's law. So we've already got this. We know what current is. It's the flow of the current, or the flow of the charge. We know the voltage is the push. And we know that resistance is the opposition, or what's pushing back. Okay, so this is another analogy. This is just like the water tower we were talking about, where it's holding all this water, and then you have the flow, which is your amperage, and then however much water there is in the one side pushing the water through is your voltage. Okay, and then of course you've got this little wheel here because you can kind of slow down that amount of flow going through by turning this on or off. Okay, so here is the anatomy of a flashlight. You don't need to write this down. It's just kind of an example. So this is what the flashlight looks like from the outside, but inside this is what it looks like. You have your D cell or your battery, and then it connects up to a switch, and then that connects to a light bulb. Okay, so this is what the schematic of that flashlight would look like. You have a battery, you have it connected to a switch, and that goes to a light bulb, and that's your schematic. Okay, it's pretty simple. The closed circuit is whenever the switch is closed and touching the 2 ends here. Open circuit, the bar is not touching the 2, so it leaves it open. But this is what it looks like. You've got all of your voltage being pushed, or all of your current being pushed through the light bulb whenever the switch is connected. So it's making a complete circuit. Okay, whenever the switch is off, there's no voltage going across because there's not a completed circuit. So
But if I touch it and touch the other one, it'll go through.
no, that would be trying to make you part of that circuit, but you're too much resistance to allow that to happen. All right. What? Our bodies are a resistor, yeah. Yep. Whole lot. Okay. So conventional current versus electron flow. This is something you should write down.
Conventional current?
Yep. So conventional current, this is your scientific current, flows out of the positive side of the battery through the circuit and back to the negative side of the battery. This was the convention established when electricity was first discovered, but it's not correct. Because what actually happens is that electrons flow out of the negative side of the battery and come back to the positive side. So this is what when they discovered electricity initially, this is what they thought was happening, and that the current was actually going from positive to negative. But in actuality, they figured out that electrons actually flow from negative to positive.
They thought negative to positive versus positive to negative.
Right. And so, well, you're going to see that this is where scientists and engineers don't have exactly the same opinions. But so conventional current says that it's positive to negative. Electron flow is saying negative to positive. That's really what you need to write down. I said conventional current assumes that current is going from positive to negative, and electron flow assumes that it's going from negative to positive.
I can kind of see that, like the positive going to the negative though.
You're going to see that we assume conventional current most of the time.
Okay, hold on.
Do what? Okay, as an engineer, when we're doing all this, we are going to assume that it's going the opposite direction because it makes all our numbers nice. If you assume it goes the other way, all our numbers become negatives.
Oh, so I've been thinking conventional this whole time though?
Uh-huh.
What?
Uh-huh. Yep.
Okay.
All right, we good? Let's move forward. Maybe. Okay. So engineering versus science. This is basically what we were saying. The direction that the current flows does not affect the current or what the current is doing. Thus, it doesn't really make a difference which convention is used as long as you're consistent. So as long as you aren't going back and forth between your two theories while you're designing your circuits, you're not going to have an issue. However, depending on what we're talking about and where we're at, you're either going to use the electron flow theory or you're going to use conventional current. Because we're in an engineering course, we're going to use conventional current, which means we're going to assume that the current is flowing from positive to negative. However, scientists will tell you that that is not accurate. This is where we may not have the same opinion. It's not that as an engineer you don't believe that that's true. It's just that our numbers need to be able to work. Yeah, and if you put it in as a negative, then it can cause a problem. What's that? It's pretty good. No, just put down we use conventional, or you can put it next to the word conventional before. You can just say we use that. Okay, so then we talked about Ohm's law. We've already kind of talked about this stuff, but this is the relationship between voltage, current, and resistance. So if you don't have that in your notes somewhere, you should probably write it down, because I'm almost positive I put that down as a test question at some point. Just knowing that Ohm's law is the relationship between those three. And then you should have this right here, that equation, I equals V over R, or V equals I times R. It just kind of depends on how you remember it. I always remember it as VIR, V-I-R, V equals I-R. But
So for Ohm's law, we just write this whole thing down.
what?
For the Ohm's law, we just write that whole thing down.
We've already written down Ohm's law information, so first I would make sure that this is in your notes, the top definition there.
I was gonna write it again, because I don't know what it's saying in my book right now.
And then make sure that you have the equation. Remember, we drew the circle with the T in it. So we had this. We had drawn that in our notebooks.
Oh, I remember that.
Yeah. Mm-hmm. What I do? God, what did I do? We watched a Cowboys game. Yeah, he won't be back till next year. I watched basically the Cowboys suffer the worst thing that could have happened. I didn't see what happened to the Browns. They got what?
The Browns got an NFL score on the Cowboys.
Oh.
Like I don't know how much it was. It was a lot.
And then I put a stereo in my truck. I detailed my truck. That's about it. Yeah, I get bored, so I have to start doing stuff. Do what? Like, I cleaned it up, made it look pretty again. Yeah, kind of like a car wash, but like more detailed. Yeah. Oh yeah, a car class. Yeah. I do like cars. I don't know what else we did. I didn't play any video games. I'm trying to think of what I did with my time, but yeah, I don't know. Do what? I do. That means it wasn't, whatever I did wasn't very important, which is probably good, because that meant I was probably just relaxing. Yep. All right, I'm going to move forward now. Okay, so here's the Ohm's law triangle, which is what I just drew. That circle, they just use a triangle instead of a circle, but it's the same thing. And then basically all you're doing is solving for each letter. So if you're solving for I, you cover up the I, and then it gives you your equation V over R. If you're solving for R, you cover up the R, and you've got V over I. And if you're solving for V, you've got I times R. That is supposed to be. If you can remember that triangle, you can pretty much remember Ohm's law all the time. Okay. It's pretty simple. You just cover up the letter you're trying to solve for. All right.
You write the value, V times V times R, right? V over I, V times R.
V over R. The only one you multiply is when you're solving for V. Okay. So this example is a flashlight that uses a 6-volt battery and has a bulb with a resistance of 150 ohms. When the flashlight is on, how much current will be drawn from the battery? So this is the type of scenario that you have in your lab. So we're looking for current. So we want to solve for current. So if you have your equation, or if you have your Ohm's law, you should have V, this is I, this is R,
Yeah.
right?
Yeah.
All right. So we're solving for I, so we cover up I, and what's our equation?
Over R,
V over R.
voltage times resistance.
Okay, and our voltage, not voltage times, voltage divided by, our voltage is 6 volts, so we put 6.
6 divided by 150.
Exactly.
Okay, Mom.
Ross, have you already calculated it? Can you give us an answer?
Yes, it is 0.04.
0.04. Is there any remaining, is that it, just 0.04?
Yes, there's more. There's more.
Okay, give me like
Uh,
2 more digits.
it's like you put an M for scientific notations,
Okay, how about if you just give me,
and an A for
Okay.
amperage.
is it 0.04
And then-
MA?
It's just,
Or is this?
No, it's 40 MA.
Okay, thank you. So this is just 40A or 0.404A. Okay, and then
Yeah.
Ross has already gone through and calculated and did our scientific or engineering notation. So he's moved this 3 spots over. So that's how he got 40. And that would be 40 times 10 to the third, or to the negative third, since it's going to the right. Right? And that's A. And then you do your SI notation, which is this part, and convert that to an M, lowercase m. Oof, that's tough right there. That's a hard. Okay. And then so you end up with 40 MA, 40 milliamps.
you lost me at the 10.
This is the notation part. So we had 0.04, and we have to move that decimal place to where we have more, or we can't have a point value. It has to be something more than 1. So we had to move it, and we have to move it 3 spots. So we went 1, 2, 3, which gets us 40.
What if you can't move 3 spots though?
You have to. You can always move it.
So, just like a 0 for the first place?
Yes. So this would be like a 0 here. Let me put a 0 there. Just like that.
All right,
The 10
Uh-huh.
square came from the, 10 3 square came from the,
Movement of the
yeah,
decimal point.
that's where we got 3 from.
Right. And you have to move in 3s, multiples of 3. Did everybody get that?
Almost on.
I honestly don't know what it's going to put up on the screen whenever I hit next. So it might clean it all up, or it might look better than what I wrote here.
All this is gonna go away.
Okay. Okay, but it gives you the same answer. Okay. Come on. There we go. So your I equals V over R, you 6 volts over 150, which is 0.04. And then we convert that to SI notation. Good? Everybody get that?
Yeah.
This is the type of stuff you're going to be doing in the lab. So for the hand calculations part anyway.
Oh no.
It's not too bad. It's a simple multiply or divide kind of question. Okay, circuit configurations. There are 2 different circuit configurations. One is a series circuit and one is a parallel circuit. Series circuit, this is the part where they write things a little bit weird. And this is where people get this particular problem incorrect all the time. So let me just explain. Series circuits have have components that are connected end to end. So one end is connected to the end of the next component. Okay, so this component end right here is connected to this component's end. This component's end is connected to this component's end. Okay, so the ends of the components are connected to another component's end. I don't know how else to explain it. The wording is where everybody gets it mixed up. There is only one path that leads through the circuit for the current to go. In parallel circuits, they have it listed down as both ends of the components are connected together. Okay, this is where it's a little more complicated, or the way that they word things is weird. So the one component's end is going to be connected to all of the other components' ends. And then the other component's end will also be connected to all of the components' ends. This way there's multiple paths for the current to flow. So this one has each component or each end connected to another end. And this one has all of the ends together.
That's pretty simple.
Yeah, except that it's worded weird, so it becomes one of those problems that a lot of people get wrong.
Yeah, I don't think so. So you think I should write it down?
I would. All right. Dang. Okay. You might even draw a little image, like a component connected to another component end. And this one you might say multiple ends connected together. You got some comments you need to read through? Ah, Hashir, yes, that is correct. Don't forget your units at the end. All right. Is everybody good?
No, no, no.
I'm hearing a lot of yeses.
I don't even hear it yet.
Series, they're all connected in a circle, component end to end. In parallel, components are connected together,
How long is time you don't?
multiple ends connected to multiple ends. All right. And here we go. All right. Characteristics of a series circuit. Okay, this is stuff you want to write down, so you can go ahead and start writing it now. Current flows through every series component equally. So if your current is 5 amps, it's going to flow 5 amps through this resistor, then it's going to flow 5 amps through this resistor, then it's going to flow 5 amps through this resistor.
Writing all down.
Yes, you need all of that. Those are the three things that are going to be the characteristics. We're going to have 3 characteristics for series and 3 characteristics for parallel. So the biggest thing is that you need to know that current does not change in a series circuit. Okay. And then the second one is your total resistance. The total resistance in your circuit is going to be this resistor added with this resistor, this resistor. Basically going to take and add up all your resistors to get your total resistor value.
So they're all bodies. Like 5, 10, 50, 20, like 20.
What are you saying?
Like they're all like.
No, that's current. Resistance is how much resistor values you have. So this one's 220, this one is 470, and this one's 1.2K. Don't forget that the K means times 10 to the third, so this is actually 1200. So then that would make this 1600, right? 1670. And then this would make it 1890. So your total resistance value would be 1890 or 1.89K ohms. And that's how you would get your total resistance. Okay, and then the third characteristic is that the sum of all of the voltage drops, that's how much voltage you lose after going through each resistor. If you add all of the voltage drops, it's going to be equal to the amount of voltage that you put in. So in this case, it would be equal to 12. And that's called Kirchhoff's voltage law, or KVL. So if you lose 6 volts here, you lose 3 volts here, that would be 9 total volts, and you have 12. So this has to lose 3 volts. Because you have to be able to say 6 plus 3 plus 3 is 12. Does that make sense? Kinda? You'll see. We're going to do some examples and you'll see how it is. Yes. Do what? How many slides? I think there's a total of like 26 in this PowerPoint. What?
Compared to most, this isn't that long.
No, that's not too bad. Not too bad. All right, so that's series circuits. Here's an example that we're going to go over. Actually, I guess we're going to do it right now. It looks like they're going to do it right now. So first thing we're going to do is calculate RT. Then we're going to calculate the current. And then we're going to get the voltages. Okay, and this is what you're going to be doing in the lab. So they already kind of went over it for us, but your total resistance is going to be R1 plus R2 plus R3. Well, R1 was 220, R2 is 470, and R3 is 1.2K. So it's 220 plus 470 plus 1.2K. Remember that this is 1200. And that's how we got 1.89K or 1890 ohms. Okay, and that's how we solved for how much resistance was in that circuit. Okay, once you have this number, you will be once you have this RT. By the way, I always like to box my answers so that I know where my answer is, so that when the teacher's grading it, they know where to look. Yeah. Uh-huh. Okay.
Oh, what you're supposed to, so like, when we got like 1.89, we did it from the 0, and then 1, 2, 3.
Yes. 1, 2, 3 from here.
1, 2, 3.
Yep.
And that's how we got 1.89.
Yes. And the K is times 10 to the third.
Okay, cool.
Yep.
See, I'm getting smarter.
There you go. Okay, so now once we have we solve for our RT, we have to solve for IT so we can get our current. Cover up the I and you should see that it's V over R. And our voltage is right here, 12 volts, okay? And then our R is what we just solved for. 1.89. So you're going to take 12 volts and put it over 1.89, and it gives you 6.34. It gives you 0.006349. And then you move your decimals over and you get 6.349 milliamps. Okay? Is that right?
Yeah.
Okay. And that's how you solve for your I. So your I total is going to be this value right here. But your I doesn't change between this resistor, and this resistor. They're all the same because your current stays the same in a series circuit. So once you solve for one, that's the answer for all of them. All right, that's why they're saying IT is equal to IR1, IR2, and IR3, because all of those are the same thing.
All the, where I in, either the,
Current.
all current the same,
Right.
unless you change something.
What?
Unless you change something in the middle of it.
Well, if you change your circuit in any of it, then it changes current in all of it. So you can't do that. Okay.
Jackson, you got a question?
Okay. The last part is to solve for the voltages across each component. And so to solve for V, you're going to use the Ohm's law again. So V is going to be equal to I times R. We know what I is because it doesn't ever change. So we already know that that's 6.349 milliamps because that's not going to ever change. Okay. So then you would take that 6.349 milliamps and multiply it times the value of that resistor right there. So times 220, and that gives you the voltage that you lose across that resistor. And then you're going to do it for the resistor over here, which is 470, to get 2.984 volts. Then you're going to do it for this resistor, which is 1200. Just here, 1200. Oh yeah. And you get 7619 volts. Okay. And these will get your voltages across each resistor. By the way, they put these little subscripts like this right here where it has like the R1 to represent that they were talking about this voltage across this resistor. R2 for this resistor and VR3 for this resistor, so that you kind of so you know which one you're solving for. Okay, so once you have all of this information, you want to make sure that you get it correct. So the last part is to do Kirchhoff's voltage law. And Kirchhoff's law is going to state that you're going to add up those three voltage drops, and they have to be equal to however much voltage we put in, which was 12. Okay, so they're adding up those three numbers that we have, and they have to equal 12, or very, very, very close to it. Sometimes you'll have rounding issues where it might be 11.9, but that's just a rounding issue. Is everybody good? Okay, that's what you would do to solve or design a series circuit in class. This is what you're going to be doing in the lab. And then, of course, in the test, when we have a test. The test won't be for probably 2 weeks. Yeah. He does? All right, let me see if I can get out of this somehow. Oh, wait, that's not what I wanted to do. Why is this full screen? Keep. I don't know why it did that. It's like it wouldn't let me go here. Jackson, do you have a question? Can y'all hear me?
I can.
I know you're in my classroom. Can anybody hear me out there?
Yeah, I can hear.
Okay. I'm just making sure. Jackson, did you have a question? Oh, I don't even see him on here anymore. Maybe he got kicked out.
I didn't kick him out.
I don't know. All right. Moving forward then. So we just finished Kirchhoff's law. So we just finished that series circuit. Now we're done. If these two numbers are the same, If they equal 12 volts, so they're both the same, then you did your work right. Okay, and that's like your confirmation. You know how they always say check your work in math? That's what you just did. You checked your work. Kirchhoff's laws make sure that, or has you checking to make sure that you did your values correct on your voltages and stuff. If these don't come out right, then you've done something wrong in your math. Yeah. VT is equal to VR1 plus VR2 plus VR3. VR1 is the voltage across this resistor, VR2 is across this resistor, and then VR3 is the voltage across this resistor. VT is your voltage total. So that's how much total voltage you started with. What they're saying is that if you're going to use 12 volts, you're going to lose 12 volts or use 12 volts throughout the circuit. You don't have any extra voltage at the end. You can't have this one only using 1 volt, this one only using 2 volts, and this one only using 2 volts, and that gives you 5 volts that it's using, but then have put in 12 volts. It doesn't work that way. Okay? Whatever you put in, you're going to use up. Does that make sense?
I was listening, I was like, huh?
Okay, well, we'll come back to that. We'll make sure we get that. All right, next one is parallel circuits. You're going to want to write these 3 things down. Yeah. Like I said, this is the hard part. Like most people, this is where we struggle, especially with parallel circuits. Okay.
So, we just trying to top part of it, right? The rest of that.
Ross, why are you muting me?
I didn't.
Oh, I see. So now you're going to try to tell me that Cam did it? Uh-huh.
I'm not accusing anybody of anything. I'm just saying I didn't do it and you were muted. Okay.
Oh, I see.
I bet you did it, actually.
Oh, you think I did it? Okay. Well, that's what Cam said too. I guess I did.
You did?
Did you actually do it? I'm actually, I don't really know. I don't really care.
Oh. Do what? Yeah, no.
Were you saying anything important?
I always say things that are important. If there's words coming out of my mouth, you know they're important.
Well, I couldn't see your mouth, so I didn't know if you were saying anything. And you also muted, so.
I must not have been saying anything important then. All right, total resistance, RT. This is the complicated one. So if you look at that equation, you can say that 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay. If that's the case, you can solve for RT and it gives you this equation, which is 1 over R1 plus 1 over R2 plus 1 over R3. Really should have parentheses here. It should be more like that, so that y'all all understand. Do what?
No, like, why can't we take your copy of this?
We're not allowed to. It's copyrighted. That's why you guys are putting it in your notebooks.
So we have to handwrite it.
That's why.
Come on, PSW.
All right, the sum of all the currents in each branch is equal to the total current. So this particular case, you're going to add up the current that's going down this row, the current that's going down this row, and the current that's going down this row, and you're going to add them all up. I guess they're columns, not rows, but you're going to add all those up, and that's going to give you your total IT, or your total current.
I didn't write down the, what is it called?
I don't know.
The 1 equals R.
Bless you. Yeah.
What's the first gas station snack or candy you ever had?
That I ever had? I have no idea. I have no idea. Like, that was so long ago.
This was like 7 years old.
First, probably an icy. Yeah. Because I imagine that was something that my mom would have taken us and gotten. I don't know, what do they cost now? I haven't had one in a long time. 98 cents. They'll probably cost more back then to get an icy. Yeah, I don't know.
You got muted again.
All right, and then we were here.
There we go.
All right, stop muting me. All right, otherwise I'm going to take away all your privileges, and then you'll have to be here on time, otherwise I won't let you in. Because once I start, I can't tell you you're getting in here. So, all right. So those are the three things we're doing: resistance total, voltage across each component, and then your current total, and then your KCL, or your Kirchhoff's current law.
Right.
Nope, this is what we're doing right here. Okay, so to find your total resistance, this is the part that people mess up on. It's usually a math issue. So make sure that you put it into your calculator correctly. My suggestion is to do one term at a time, 1 over R1, get that value and write it down. Then do the second one and get that value and write it down, and then do the third one, get that value and write it down. Then you can add those three values together and take 1 over that. That's my suggestion so that you don't get this incorrect, okay? Or so that you get this correct, okay? So the first one is 1 over R1. R1 is 470 ohms. So it'll be 1 over 470. Does anybody have a calculator? Yeah, you want to calculate it. 1 over 400. 0.0025. That sounds right. There's no way to like write on this. Oh, I didn't want to do that.
Yeah, we got 2 more slides left, and then we're done.
Okay, so we'll say 0.0025. Okay, then we have the next one, which is 1 over 2200. Mm-hmm. 0.000. Zero. 4545 repeated, looks like. So I'm just going to stop there. And then the last number is 1 over 3300. Okay, 0.000 because it's got a K, and then it's 303. Okay, so we'll just do 30. Okay, so you're going to add all those up. Yeah,
Add all these up?
yep. .00, and then you got 5, 7, 9. No, 7, 5. That's 12.
0.00325.
325. That sounds right. Okay. So now you have this, which is this number right here. This number goes right there. Okay. So you're going to take 1 over that number to get your resistor value.
To do what?
Take 1 over the number that you came up with here, and it should give you a resistor value. Now, it won't be exact. It won't be precise because we have rounding issues that we went through. You got what? 3 point what? 307. Oh, 307.7. So you could call this 308, and that's probably fine. Okay, either way, you can see we're off by quite a bit there. It's probably somewhere in this area because 1 over 470 does not look like it would be 0.0025. It's actually 0.0021. So this number here would be incorrect, which is going to throw your numbers off. We had some rounding issues here, and then this one also has some rounding issues. So, but anyway, that's how you would get your resistor value. Okay, and that's how you would get your total for your resistor. This is where most people go wrong. But that's how that would work. Okay, and then the voltage that you start with here is always going to be the same voltage that you have going down each path. So 15 volts is what's coming down this way. So the voltage across this resistor is going to be 15. The voltage across this resistor is going to be 15. And the voltage across this resistor is going to be 15. Because voltage never changes. Whatever you put into it is what you're going to get for each column. All right, which is what they're saying right here. Okay? All right. So then the next part is to go through and solve your I for each column. So since we know that our voltage never changes, your V is always going to be 15. So 15 over 470 gives you this value, 31.9 milliamps. 15 over 2.2K gives you this value. And then you have 15 over 3.3K gives you this value. And since we solved for our RT earlier, we take 15 over the value of our RT to get our total IT. This is our total IT. This is our total. Okay, so this number, and this number should add up to this. 31.915 plus 6.818 plus 4.545 should get you to that number. Does that make sense? And then that's how you'll solve, that's how you'll do Kirchhoff's current law, which you're basically going to take all those numbers and add them together and make sure that they are the same as what we solved for our IT. And if that's the case, then you know you did your problem right. Does anybody have questions?
When we do the live video.
Yeah, I'm sure. We'll have lots of questions when you do the lab. What time? Yeah, we're going to start it.
Today?
Yeah, right now. Because we got, what, 30 minutes? Not quite? Yeah.
3:15 we did, I believe.
Because that's it. That's the end of the PowerPoint. This just talks about KVL and KCL, which we've already talked about. And then that's it. Okay, so I'm going to discard that. I'm going to go back here and stop recording.